So last week, I think we have been covering the spectral theorem for the Hermitian matrix and other properties such as principal axis theorem, right? So how to make a unitary matrix out of the eigenvectors. And actually, I had started but haven't finished the other part, that the older theorems that we have been learning, that the eigenvalues are real numbers and all the eigenvectors are orthogonal to each other, and the outer product of eigenvectors form completeness relations, and spectral theorem and principal axis theorem. And all those properties apply to when the matrix is Hermitian. But what if it is not? So let's try to consider the general matrix. Oh, something is hard. My iPad doesn't recognize the pen, so let's just try to. Now it works. So whenever I restart the iPad, apparently it doesn't recognize the pen. All right. So when A is such as 11 minus 5 minus 2, 10, can you say that this matrix is Hermitian? No, right? Answer is no. Because when you take a dagger, 11 minus 2 minus 5, 10, apparently it's not A, right? So A is not Hermitian matrix. Let me just. But we can form a new matrix, M, A, dagger A. Then definitely so this matrix is Hermitian. So M is Hermitian. So we can see that explicitly that M is A dagger A is 11 minus 2 minus 5, 10. 11 minus 5 minus 2, 10. So the first element, 11 times 11 is 121 plus 4. Am I loud enough? Can you hear me well? If you have any difficulty, just let me know. 121 plus 5 is 125. And this. Minus 55 minus 20 is minus 75. This is again. Minus 55 minus 20 is minus 75. The last element, 25 plus 100 is 125. So that is 125. Is same as M dagger, right? So M is Hermitian. Of course, it is expected from the definition of M, but we can also, it wasn't hard to see that this matrix is summation explicitly by from the building the explicit matrix. So next step is we can find the eigenvectors and eigenvalues. So m minus lambda I 125 minus lambda minus 75 minus 75 125 minus lambda is 125 minus lambda square minus 75 square is 125 lambda plus 75 lambda minus 75 is equal to 0. So lambda is 50 and 200, right? So we can say lambda 1 is 50, lambda 2 is 200. So normalized eigenvectors. Case number 1, lambda 1 is 50, then m lambda 1 is 50 lambda 1. So 125 minus 75 minus 75, 125 AB. Say, you can say lambda 1 is AB equal 50 AB. So 125A minus 75B is 50A minus 75A plus 125B is 50B. So that means A is equal to B, right? So without much difficulty, we can just write down normalized eigenvector lambda 1. Square root of 2, 1, 1. Lambda 2 is 200. So m lambda 2 is 200 lambda 2. You can also say lambda 2 is AB. 125 minus 75, 75, 125. AB is 200 AB. So 125 A minus 75B is 200A, and minus 75A plus 125B is 200B. So B is equal to minus A. So we can say lambda 2 is the square root of 2, 1 minus 1. We can summarize m is 125 minus 75, 75, 125. Lambda 1 is 50. Normalized eigenvector is square root of 2, 1, 1. Lambda 2 is 200. And normalized eigenvector, square root of 2, 1 minus 1. So before I proceed, let's just review some concept that this psi is A, some any vector free, then we know that any vector free, the inner product of any vector with itself is always positive, right? So psi is nu a dagger a nu is nu m nu is always positive. So we can say M is a positive vector, positive matrix. Then you can form a square. M is this is spectral theorem. Positive matrix means all the eigenvalues are positive. Then we can define the square root of matrix M. Then for some unitary matrix, U, A can be written as a U square root of M. This is called polar decomposition. So any matrix A can be represented as a product of some unitary matrix that we are going to define. Some unitary matrix that we are going to define and square root of A. So how to define the unitary matrix is the next step. So actually this is a little bit difficult subject. So I'm going to progress as slowly as possible. And if there is any step that you don't understand, then you can just ask a question and stop me, then probably I will repeat. So building unitary matrix. So we define psi I such that is A times lambda I. From this we built normalized I by dividing psi I. One of the property we want to know is also normal to each other. Let's check. Ej, Ei. This is lambda j, A dagger, A, lambda I, divided by square root of lambda I, lambda j, right? This is what? This is m, right? So we can say that this is square root of lambda I, lambda j, lambda I, lambda j, but they are orthogonal to each other, right? So this is orthonormal matrix. So this is delta ij. So it turns out to be simply delta ij. The denominator 분자 is lambda I. Denominator is square root of lambda I, lambda j. But this vector is only non-zero when I is equal to j. Then this lambda I, lambda j, same as lambda I square. And square root of lambda I square is lambda I, so they cancel each other. And this delta ij. So you can see that this matrix also orthonormal basis. Then we define U as follows. I'll just let you copy the step. Okay. Then we can define U as following. Lambda I. We define U this way. And then see what it's U square root to m lambda I. J square root of lambda j, lambda j, j k, lambda k. This is what? Square root of lambda I, a, lambda I, right? Square root of lambda j, lambda j, lambda j, lambda k. I, j, square root of lambda I, a, lambda I, lambda j, lambda j, lambda j, lambda k, square This is I. So this is Kronecker delta ij. It survives only for I, A, lambda I, lambda I, lambda K. We can put A out of this, lambda I, lambda I, lambda K. So this part is actually I, A, lambda K. But actually we can substitute. So we started only for lambda K, but this works for any free, right? So we started with lambda K, but it should work for any free. So we can say that A is equal to U square root of M. And let's see actually if this works. So let's start with M. Lambda 1, 50. Square root of lambda 1 is 1. Lambda 2 is 200. Lambda 2 is square root of 2, 1 minus 1. So square root of M is square root of 50, lambda 1, lambda 1, square root of 200, lambda 2, lambda 2, right? Square root of 50, 1 over 2, 1, 1, 1, 1, plus square root of 200, 1 over 2, 1 minus 1, 1 minus 1. Fifty is 5 square root of 2, right? 1, 1, 1, 1. 200 is 100 times 10 times 10 times square root of 2 divided by square root of 2. 1 minus 1 minus 1, 1. Square root of 2 over 5, 1, 1, 1, 1. Square root of 2 over 10, 1 minus 1 minus 1, 1. So 5 square root of 2, 3, minus 1, 3, right? square root of 50, 250 is 25 times 2, that is 5. 2, square root of 2 divided by 2 is 5 over square root of 2. It's 100 times square root of 2 divided by 2 is square root of 10. 1 minus 1. So this is, you can factor 5 over square root of 2, 1, 2, 3, right? 1 minus 2 minus 1. Now 5 square root of 2, 3, 3 minus minus. Okay, 5 divided by square root of 2. Build the unitary matrix. Psi 1 is 8 times lambda 1. A was square root of 2. 11 minus 5 minus 5, 10. 1, 1, right? Square root of 2. 11 minus 5 is 6. Minus 2 plus 10 is 8, right? So epsilon 1 is square root of 2 times square root of 50. Six A is 1 over 10. 6A 1 over 5. 3, 4, right? E2 square root of 200. 11 minus 5 minus 2, 10. Square root of 2, 1 minus 1. 400 is 20, right? 11 plus 5, 16. Minus 2, minus 10, minus 12. So 10, 8, minus 6, 5, 3, 4, minus 3, right? E1 is minus 5. So let's just double check if I proceed. Square root of 50, 1 over square root 8 times psi 1, square root of 11 minus 5 minus 5, 10, 1, 1. 11 minus 5 is 6, minus 15 is 8, right? Divided by square root of 50 is 1 over 10, 6, 8 is 1 over 5, 3, 4, right? E2, 1 over square root of 200 times 11 minus 5, 10 minus square root of 2. So the square root of 400 is 1 over 20. 11 plus 5 is 16, minus 2 minus 10 minus 12. So it's 10 over 8, 6, 5 over 4, 3, right? So U matrix E1 lambda 1, E2 lambda 2, one over 5 square root of 2, 3, 4, 1, 1, right? Plus 1 over 5 square root of 2, 4 minus 3, 1 minus 1. So 5 square root of 2 is common. 3, 3, 4, 4 plus 4 minus 4 minus 3, 3. So 5 square root of 2. 7 minus 1. This is 1. 7. So U is, let's check this unitary matrix is unitary. Let's just check, double check before I proceed. So E1 times lambda 1 is square root 5, square root of 2, 3, 4, 1, 1, plus 5 square root of 4 minus 3, 1 minus 1. So this is 3, 3, 4, 4. This is 4 minus 4 minus 3, 3, right? So 5, one of the 5 square root of 2 is common. So 7, 1, 1 minus 1. So let's check U. Seven minus 1, 1, 7. U dagger. 7, 1 minus 1, 7. So U dagger. 25, 50. 7, 1 minus 1, 7. 7 minus 1, 1, 7. 1 over 50. 50, right? This 0. This 0. This 50. So I, right? So we can see that U is a unitary. Anybody remember what was root square root of M? Let's go back. Square root of M. 3 is 3 minus, right? 5. So let me double check. So let's check. U square root of M is 5 square root of 2, 7, 1 minus 1, 7, 5 square root of 2, 3 minus 1 minus 1, 3, 1 over 2, 22, minus 7, oh sorry, this is minus, this is plus. So this minus 10, 3 minus 4, minus 4, 20. It turns out that 11 minus 5 minus 2, 10. This is what's A, right? So any matrix A can be represented as product of unitary matrix and square root of a matrix. So this is actually very important property that's used in quantum computing. So this covers the material that we need to, learn this method about linear algebra. And I'm going to move on to the next topic, that is differential equation. But I guess some of you may not have a proper preparation for the calculus, so I'm going to review a little bit. So before I proceed to the next topic, any questions? Well, perhaps you can take a break for a few minutes and starting with a new chapter. What about that? So let's say 5 minutes. For the next few weeks, maybe, I don't know, a month or so, probably the rest of the semester, we are going to cover differential equations. But before I proceed, we are going to have some review of calculus. Because some of you may not have a proper preparation for how to differentiate integration, so calculus properties. So today and maybe next week we are going to review some of the basic principles. So we are going to study the function. Say y f x. Probably you learned this function maybe in the middle school. So this is input called independent variable. This is output, dependent variable. So function is basically a rule that assign y for each x. So there is only one y, but there can be several different x. So one good example is a vending machine. You put coin, the coffee came out, right? One coin for one coffee. Maybe there are other special coffee, right? So for this special coffee, you put 2 coins, still you get 1 coffee, right? For normal coffee, you just put 1 coin, 1 coffee out. But there is no way that you put 1 coin and 2 coffee out, right? There's no way. So output has to be always 1. Input can be 1 or whatever. Those are the functions. Continuous. This is very important property. We say a function is continuous at x equal x0 if fx minus fx0 smaller than epsilon for x0 delta and epsilon delta is smaller than is greater than 0, but small number. So continuity is probably the most important property to define before we can define the derivative of a function. So this is very simple. When x minus x0, x naught is the distance between x and x naught is less than some delta, then fx minus fx0 is less than some epsilon. For whatever epsilon delta greater than 0, and they are small numbers. So let's say if can you say that this function is continuous? There is some discontinuity at x now, some jump. Say this is a. If there is a sudden jump of a function, can you say this function is continuous? It's not continuous, no. This is not continuous. How about this function? This function is continuous, right? But may not be differentiable. But not differentiable. So those are two extreme examples of functions. It is not continuous. The other one is continuous but not differentiable. Now we define derivative. So continuous function. So can you understand what is continuous function? So when x is changing a little bit, then function actually changes a little bit. In that case, we say So the function is called continuous. And then derivative. Oh, what happened? Okay, so derivative. X. We take the limit. Fx, so condition when fx is continuous at x equals 0 and 1 is equal to 2, then we say fx is differentiable and we call dx dfx as a derivative. Korean derivative is 미분. So differentiate is 미분하다. Derivative is 미분, differentiate is 미분하다. So just the limit. It's two different limits. One is x plus delta minus fx, and fx minus fx minus delta. If this 1 and 2 are the same, then we say this function is differentiable, and we call this dx as a derivative. Probably you have memorized most of the derivative appearing in 수학의 정석, right? So this time let's just try to see from the very basic definition. After we derive the derivative, then of course it is useful to memorize. But don't rely on the memorization because on quiz you are allowed to bring cheating kits, right? You don't have to memorize. Just remember the basic definition. So I'm going to consider the examples throughout the class today. So when fx is x, then fx plus delta minus fx is what? X plus delta minus fx, right? Oh no, fx is delta. This is x. What is that? X plus delta minus x is simply delta. So if you divide delta over f x plus delta minus fx is delta divided by delta is equal to 1, right? So this is. So dx dx, you take the limit, delta goes to 0, delta x plus delta minus fx is 1, right? So when f is just simply x, then derivative is 1. Now you already know this, right? How about x squared? Delta square, right? X square plus 2 delta x delta square. So you divide by delta. What do you get? Delta over x square plus e 2 delta x plus delta square minus x square delta over 2 delta x plus delta square is 2x plus delta. So if you take the limit, what do you get? Simply 2x, right? So two x. Of course, you have memorized during your high school days. How about x cubed, x to the cube, x to the 3? Fx x to the cube. Can you expand this using binomial expansion? X to the cube, 3 x squared delta, 3x delta square plus delta cube, right? So f x plus delta minus fx, simply 3x squared delta, 3x delta square plus delta cube. So if you divide by delta, what do you get? Simply 3x squared plus 3x delta plus delta square. Now derivative is that you take the limit setting delta equal to 0, right? So if you take the limit, three x squared, the rest of it just 0, right? Okay. So you can make a table. I will probably have memorized this too, but so we can continue this. Let's say fx dx dfx. And fx is x. What is the derivative? This is 1, right? And this is x squared. We have 2x. And this is x cubed. We have 3x squared. So we can continue, I guess. What would be x to the n? N times x to the n minus 1, right? So for this, we can use binomial extension, but so can you believe this now? You have a belief? When we have xn, then derivative is n times xn minus 1. I haven't derived this. I only derived up to the 3 terms. But if you continue, you will get this, right? Or if you cannot believe me, you can just read yourself using binomial extension as whole. So maybe this is a good homework problem. So polynomial is easy. Finding the polynomial, derivative of polynomial is very easy, right? How about 1 over x? That is a little bit more difficult. And fx 1 over x. Probably you have memorized this as well, right? You know the answer. Minus 1 over x squared. But it wouldn't hurt to derive from the first principle. X plus delta 1 over x, right? So this is x times x plus delta, x minus x plus delta, minus delta over x plus delta. So delta over f x plus delta minus fx minus x plus delta. So if we take the limit, delta goes to 0, delta f x plus delta minus fx simply x squared, right? We just simply put delta as 0. So we can continue this as well. So dx 1 over x squared. How about 1 over x squared? You know that you probably have memorized it. Minus 2 divided by x cubed, right? So we'll just do one more term. Can I continue? One over x squared. So f x plus delta minus fx is x plus delta square of 1 over x squared, right? Is minus x squared, x plus delta squared, x squared minus 2x delta minus delta squared. So this cancels each other. Delta over f x plus delta minus f of x is x squared, x plus delta squared minus 2x minus delta. So if you take the limit, what do you get? Delta goes to 0, delta over f x plus delta minus fx is minus 2x, x squared, 2 over x cubed, right? We simply put delta as a 0 here. And put delta 0 here, right? 2 over x cubed. So probably you have memorized this during your high school days, but actually it can be derivable. So I'm going to put another table. Can I go on? Time to copy. Am I going too fast? Okay. So another table. Fx 1 over x squared, right? 1 over x squared, 2 over x cubed. So we can continue. 1 over xn minus n over xn plus 1. I only showed two cases. So this is this is 1, 1, 2, 2. We have one more order in the denominator. So when this is n, we have n in the denominator and n plus 1. So far is the easiest part. How about square root of x? You know the answer, 1 divided by 2 square root of x, right? So I'm going to follow Newton's original approach. (1645). Newton knew the following formula. let's check. Anybody has a calculator? Can you calculate? Anybody has a calculator? 1.1 square root. You can say in Korean. 1.04 88 088 Okay. When delta is 0.01, how about this? One point 0 0 04 004 Thank you. 004죠. So when delta is going 0, is getting 1 point delta over 2. That's what Newton actually did. About 400 years ago, Newton calculated square root, and we found that continuously making smaller number, we found that 1 plus delta to the 1 half goes to 1 plus delta over 2. So actually, for the analysis, it's nice to remember that 1 over n actually goes to 1 plus delta over n. Because delta goes to 0. Newton knew this result about 400 years ago. So we are going to use this result. So this is very useful if you useful knowledge if you know this really. You can approximately calculate any square root. Let's say fx is square root of x. Then fx plus delta minus f of x is square root of x plus delta minus square root of x, right? This is x, 1 plus delta over x minus square root of x, right? You can say square root of x times square root of 1 plus delta over x minus square root of x. For sufficiently small x, for small delta, it becomes square root of x 1 plus delta over 2x minus square root of x. Delta over square root of x, 2x, 2 square root of x delta, right? So delta over f x plus delta minus f of x is 1 over 2 square root of x. So if you take the limit dxt delta f x plus delta minus of fx square root of 2x, right? I think in high school days you just memorize, but now you can see how this is derived. But of course, it's better to memorize it again. But at least you can see how this strain formula can be derived from the fact that what Newton discovered about 400 years ago. About 200 years ago, the French mathematician Napier discovered another interesting property. That if you take the limit this is called E, Napier's number. 2.718, etc., etc. So maybe you can see that delta is 0.1. What happens? 1.1 to the 10 is can you say 2.69 or something? point 2.2.59 374, etc., right? How about thank you. Eventually it will become this Napier number. So that is basically what? If you deposit your money with your 1% interest and money for 100 years, then you will get 27 times the original money you deposited. So if you have 10% interest rate for 10 years, roughly 26 times. So this number is also very interesting properties. And using this property, you can define the derivative of a logarithm. Natural log. Of course, derivative is, you know the answer, 1 over x, right? F x plus delta minus fx ln x plus delta minus ln x. This is x plus delta one plus delta over x, right? So delta over f x plus delta minus fx is 1 over delta ln 1 plus delta over x, right? Here we can do nothing, some interesting things. Right? If I multiply x and divide by x, it's the same thing, right? I haven't done anything. So you can move this to here. If we take the limit, delta goes to 0, delta over f x plus delta minus f of x equal to 1 over x ln 1 plus delta over x, x over delta. This becomes what? Epsilon e, right? So log e is 1, so it becomes 1 over x. Something is wrong. So in your high school days, you memorized many different derivative formulas. But actually, those formulas can be derivable. But after we derive this, we have to memorize it again. But still, it's better to know how it is derived than just memorize it without any prior knowledge. So there are a few topics we can cover, but for some of you might need the time to digest the material that we covered today, so a bit early, but I'm going to stop here today. But I advise you to review the derivatives that we studied today, because some of you may not studied calculus properly or in-depth knowledge. Okay, so see you next week. 이게 7이라고? 어? 6번째?